Water blasting from a turbine runner carries massive kinetic energy. If that high-velocity fluid simply drops into the river, that remaining power is wasted. To harvest this residual energy, engineers attach a specific recovery component directly to the exhaust. It's called a draft tube. On a real-world reaction turbine, it's this prominent red cone-shaped component bolted directly beneath the blue casing. The wide top flange connects exactly at the runner exit, catching the water the instant it leaves the turbine blades, and routes it downward. Crucially, the bottom opening of this tube does not hang in the air. It must sit completely submerged below the water level of the downstream discharge area, the tail race. A sealed, airtight water column maintains a continuous pull on the runner, actively manipulating fluid pressure to extract additional mechanical work. As water forces through the turbine's guide vanes and spins the runner, its pressure drops continuously. This diagram maps flow down the diverging draft tube. Its cross-sectional area steadily increases. Low-pressure water at the runner outlet must overcome the higher-pressure tail race below. By widening, the tube drops fluid velocity, increasing pressure above atmospheric before exiting. How exactly does a pipe that gets wider maintain a continuous subatmospheric vacuum at the top, while simultaneously pushing against atmospheric pressure at the bottom? By tracking the fluid's energy state mathematically from inlet to outlet, we can prove that this expanding geometry guarantees a pressure drop at the top, maximizing total efficiency. To track the energy through this system, we rely on Bernoulli's equation, which dictates how energy is conserved in a steady fluid flow. We apply this equation from Section 1's inlet down to Section 2's outlet. Setting the datum at Section 2, the inlet's elevation is height hs plus submerged depth y. At the outlet, we also account for friction loss, HF, along the walls. Because the bottom is totally submerged, outlet pressure at Section 2 is locked to the environment, atmospheric pressure pushing on the tail race surface, plus the hydrostatic weight from submerged depth y. By locking in these rigid physical constraints, submergence depth and atmospheric weight, we establish the mathematical anchors required to isolate the tube's internal forces. Look at the primary Bernoulli equation, balancing Section 1 against Section 2. On the right, we replace the outlet pressure head with our known boundary conditions, the atmospheric pressure head plus the submerged depth, y. Notice the elevation variable y appears on both the left side for inlet elevation and the right side for tail race depth. We algebraically cancel these y terms entirely. To isolate the pressure state at the turbine exit, P1 over rho g, we move the inlet's kinetic and elevation terms over to the right side of the equation. Grouping these terms yields a clear relationship. Inlet pressure equals atmospheric pressure minus the structural height minus a bracketed term containing the kinetic energy difference and friction losses. Here is where the geometry of the physical hardware completes the proof. Remember that the draft tube strictly diverges. According to the principle of continuity, because the pipe's area increases, the fluid's velocity must decrease. Therefore, the velocity at the outlet, v2, is strictly less than the velocity at the inlet, v1. Because inlet velocity v1 is larger than outlet v2, the bracketed kinetic term yields a positive number. Real-world structural height, hs, and friction loss, hf, are also inherently positive. The mathematical reality is clear. The equation takes normal atmospheric pressure and subtracts a series of strictly positive numbers. Therefore, the resulting inlet pressure is mathematically guaranteed to be less than atmospheric. The proof confirms our thesis. By slowing fluid through a widening cone, the draft tube's geometry directly generates a subatmospheric vacuum at the turbine exit. In a laboratory, a perfect vertical cone is ideal, but out in the field, excavating hundreds of feet straight down into the bedrock beneath a massive dam is often structurally impossible. To navigate these extreme spatial constraints, engineers have developed variations on the draft tube geometry. While the conical draft tube provides optimal symmetric flow, the simple elbow tube forces the water to bend horizontally, drastically reducing the vertical excavation required. The draft tube with a circular inlet and rectangular outlet takes this further, altering its entire cross-sectional shape as it bends to cleanly integrate with standard concrete tail race canals. The Moody spreading tube utilizes a complex central cone to aggressively divide and spread the water, preventing severe flow separation in shallower installations. Yet, through all these radically different profiles, they share one strict, non-negotiable architectural rule. Regardless of the bends or shape changes, the total cross-sectional area strictly increases. Environmental barriers may dictate the path the water must take, but the mathematical law of divergence must be preserved to maintain the required vacuum. Proving the vacuum exists is only half the engineering challenge. We must also measure exactly how well the tube performs its energy conversion task. This measurement is formalized by a strict metric, draft tube efficiency. The numerator calculates the actual work done. It represents the real-world conversion of kinetic energy into useful pressure head, minus the unavoidable friction losses. The denominator provides the baseline. It represents the total potential kinetic energy delivered to the inlet, the absolute maximum amount of energy available to recover. By maximizing this ratio, engineers ensure that high-velocity kinetic energy does not simply wash away downstream unused. The total power output of a reaction turbine depends on this specific geometry. The calculated expansion of the draft tube is the primary mechanism for recapturing kinetic energy that would otherwise be lost to the river.